How's it going, everybody? And welcome to our CEF concepts video. This video we're going to take a look at the different CEF concepts that there are out there and get an idea, a ballpark range idea of what's going on with CEF and how it actually works. As I'm explaining how it works conceptually, I've actually got a little setup down here that I'll explain how polarization and the different hashing algorithms work here in a minute. But I want to go over, and I've also got GNS3 pulled up. I got a router booted up, and I'll show you what CEF looks like and some of the things you can look at when you're dealing with CEF. But I want to cover just real quick the different aspects to CEF and how they work and stuff like that. So again, I mentioned in the iOS and iOS XE video that if you'd like the OneNote document, I can definitely get that for you, as well as any other type of the .NET file for GNS3 if you'd like that as well. So CEF, there's four components to it. We have the rib, the fib, the lfib, and the adjacency table. So the rib is the routing table. Okay, the fib is the forwarding table, which is this is layer 3. This is going to be layer 2. The lfib, this is going to be the forwarding table for your label information base for using MPLS. And then we have the adjacency table. The adjacency table is going to be where all of the layer 2 info for the next hop is located for everything that's associated for every subnet that's in your entire network. Now, the rib is a data table stored in a router or network computer. It lists all the routes to a particular network destination, and in some cases, well, in our case, the metrics or the distances associated with those routers. Now, the reason I'm reading this is because of the fact that it's a definition that I found on Wikipedia. So, the routing table contains information about the topology of the network immediately around it. The construction of the routing table is the primary goal of the routing protocols. Static route entries are made in a routing table by a non-automatic means. Static meaning you have to go in there and physically type in, and the command for Cisco iOS is IP route, the destination, the length, and how to get there. So, how to. So, the idea behind that is if you want a dynamic routing protocol, so you want to have a IGP, or an interior gateway routing protocol, OSPF, EIGRP, RIP, IS to IS, which we will be talking about all of these routing protocols in detail coming up shortly. I want to get the conceptual parts done first before I dive into that. You're going to use an IGP for dynamic, or you're going to use static routing. You might use floating statics, or a floating static. You use the same command up here: IP route, destination, the link, the subnet mask that matches that link, that destination, and how to get there, whether it's the outgoing interface or a next hop IP address. And then you're able to add in the administrative distance. So if you don't want a route to be in the routing table right now, if another route gets removed from the routing table, the floating static route will automatically be popped in there because the original route was taken out or withdrawn because of some sort of routing issue. Now basically a show IP route is the fib, which is a collection of best routes from each rib. So each routing protocol will have an associated rib with it. All routes for BGP will have a routing base, as would all OSPF routes. So it's going to be a database. So with OSPF, it's going to be the OSPF database, which if you do a show IP OSPF data, you're going to get the output of what's going on in there. Now the fib, or the forwarding information base, is similar. And what this looks like, it says right here, let me move the mouse out of the way here. CEF uses a forwarding information based to make IP destination prefix-based switching decisions. The fib is conceptually similar to the routing table or information base. It maintains a mirror image of the forwarding information base contained in the IP routing table. When the routing table topology changes, or when the routing or topology table changes occur in the network, the IP routing table is updated. So basically what that means, and you guys are smart, you probably can figure it out without me telling you, but you take the rib and copy that down to the fib. And what you end up doing is you create a table of, you have destination, you have, actually let me bring it up down here. You have the prefix, which is what you're trying to get to. You have the next hop, or how do you get there, and the interface, or where is it going to go, and the interface is how's it going to get there. So this information right here, all this prefix information right here, this is going to be something that's either directly connected to your device. So like all these, if you notice, we have the 0000, so like the default route, because 0 falls inside of the /8. We're also going to have a /32 for a host route, and we're going to have the loopback, we're going to have the link local multicast, and then we're going to have the administratively scoped, and then we're going to have the all host broadcast. All of these right here are either going to be directly connected to the device, or something it knows how to get to via a routing protocol, something to that effect. The next hop is going to be what you do with it. So the no route means that there's no default route configured. Receive means it will take it. Drop means it will drop it. So depending on where it leads it, it will determine how CEF will forward it. Then we have how will it get to where it's got to go. What interface will it leave on? This will either be a physical interface or a logical interface. Physical meaning fast Ethernet, gigabit Ethernet, serial, packet over SONET. What's another one? Fiber optic, where a logical will be a loopback, which you would never send traffic out a loopback, or a VLAN interface. So interface VLAN 10, for instance. So that's where this comes into play. So this right here is a 7200 series router, and basically what you're going to be running with it, if we do a show ver include iOS, we are running 7200 series router running version 15.2 for M2. So this is what you want to be running. If you can get a hold of this iOS image, I would highly recommend you do that so that you can follow along with everything we're doing. So now that's the fib. Now we have the adjacency table. The adjacency table is going to be the next hop information. Okay, so that's going to be the layer 2 info for the next hop. So if we have a router here and we have a router here, what this guy is going to do is it's going to ARP out to this guy and say, I need your layer 2 info. That could be the DELC, that could be the label, that could be the MAC. It doesn't really matter as long as it's a layer 2 address that this guy can send back to him, and he can populate the next hop information with that information. And then what ends up happening from there is the interface is then filled in. So it'll be whatever this interface is, whether it's a fast E, gig E, serial. It doesn't really matter what the outgoing interface is, as long as it's reachable. Basically what ends up happening is if you go out and you ARP, so you say, I know the IP address, I need the layer 2 information. If you ARP and you don't get a response, that means that either this interface is physically down, admin down, or it could be line protocols down, so physically it's connected, but you may have a, this side right here might be a HDLC, this side could be PPP, and you have a layer 2 mismatch. Any type of layer 2 information where you have an HDLC and PPP, that's going to be serial encapsulations. Normally, if you set ARPA, which is going to be what you see normally, that's not going to affect anything. As soon as you do a no shut at this interface level, then that's going to bring it up. Now, if this guy right here was associated to, say, VLAN 10 originally, but now is not associated to a VLAN anymore. Maybe it's in VLAN, it's a switch, and you took that port out of a VLAN. It's not going to go anywhere but to no VLAN. So if you were to do a show, run, interface, whatever, it's not going to show you the VLAN that it's in. If you were to do a show VLAN, that port's not going to show up in any of the VLANs that are configured. You would have to physically go to the interface level and type in switch port, access VLAN, whatever port. Now if it's a router, you're not going to be able to do that. So it's either going to be there or it's not. So unless you're dealing with a sub-interface and you're doing inter-VLAN routing on a router on a stick, and then you'd have to physically go to the interface and tell, when you're actually, take one step back, if you're going to do router on a stick, you have to tell encapsulation.1q and then the VLAN ID. And if you don't specify this information, it's never going to take in Cisco iOS. So now, when it comes to the LFIB, this is going to be used with MPLS. And we'll get into MPLS quite heavily a little farther down the road. But what LFIB is, it's a label forwarding information base. It's a data structure and a way of managing forwarding in which destinations and incoming labels are associated with outgoing interfaces and labels. So I don't have MPLS running in my network, but if I did, I'd be able to show you what that would look like. So you would actually see, I believe the command is MPLS LFIB, is it? Or is it, no, it's forwarding table? And then that would tell you what interface, what label, because then you would have like a, I'm trying to think off the top of my head here. It's something to the effect of, you'd have interface, label, interface, label, and you'd have the incoming interface, so fast0/1, the label associated to it. So 17, the interface that's going to go out is going to be serial 1/1, and then the label is going to be 22. Now, if you see a pop, then that means this is going to be the next to last device until it goes down to the IP routing. If it says push or swap, that's going to be one of the other ones. So push means you're going to add a label to it. So it's maybe it's a PE, and you have a CE over here, and the CE is sending traffic to the PE, and you need to add a label onto the front of this packet. So it's label switch at this point. A swap could be a PE to P router to PE, where you would end up sending traffic labeled. So it'd be labeled here. You'd send it this way. As soon as it would come in this guy, so you would swap this label to this label as it's traversing from the incoming interface to the outgoing interface, something to that effect. So it would keep a database of what's where and how it's being applied. That's the general idea behind the LFIB and the way it works. So at the end of the day, when we get into MPLS, I'll go into much more detail on how this actually works and the different ways you can look at it. At the end of the day, it's actually very straightforward in how it actually works. But knowing how it actually does its job is going to be the complicated part. Now, I've covered this pretty quickly. So when we get into more of the other topics that we're going to go through, so when we are actually getting into routing and I show you how the forwarding works and I actually get into an IP routing, I'll go into much more detail on how it actually does a lookup process and how the different switching processes work. Because realistically, CEF is just a switching process. So if I was to come down here and explain this real quick, we have a router, we have all these interfaces, and we'll go to another router, and then we'll have another connection here. The idea is very simple. When you have an incoming interface, so we have traffic coming in, this guy right here. When traffic comes in, there's a lookup process for the routing table to find out what interface it needs to go to, and then once the routing table determines, once the routing table says, okay, if you're going, the destination IP is x.x.x.x. If this is determined, then the routing table says, okay, well I have a way to get there. you're going to go from this interface to this interface. What ends up happening at that point is the switching process physically moves it from here to here. The CEF process is where this comes into play. It's the actual moving the packet from here to here, and then once the packet's been moved from the incoming interface to the outgoing interface, at that point in time, that's when all the other stuff happens, like the ARP process goes out. In most cases, if you're using CEF, this process, all these lookups have already been done. So the layer 2 information is rebuilt. And so whatever this information is here is applied to the outgoing interface, to the packet in the queue on the outgoing interface, and then it's rebuilt. But if none of this makes sense right now, that's 100% okay, because I'll be coming back to this in much more detail when we get to the IP routing section, because I'll want to explain how this actually works and stuff like that. So, alright, let's talk about the load balancing hash and the idea of polarization and how you can avoid it. Now, CEF, or Cisco Express Forwarding, as is what it really is a deterministic algorithm. When packets traverse the network that all use the same input value to the CEF hash, go to the right, go to the left decision is made for each redundant path. When this results in some redundant links that are ignored or underutilized, the network is said to be experiencing CEF polarization. What that basically means is it's going to take the same path all the time. By default, the source IP and destination IP are used to determine the forwarding. This is how CEF can polarize to prefer one path and underutilize another link. This can be changed by modifying the load balancing hash as to how CEF will choose how to forward the traffic. So now that we're on this topic, let's explain how this works. Let's say, for instance, you have a destination over here that you want to reach. So you have a host attached to a computer. We're just going to draw an old-fashioned computer there. So right here we have host 1 and we have host 2. Host 1 wants to go to server 1. The idea now is that host 1 is going to go up the network to there. So he has all these other redundant links that he could use to get there, but he's not going to, because of the fact that the way that CEF set him up, that's how it's going to go. Now, host 2 also wants to go to server 1. Now, let's assume for a minute that every link here is live and active and should be used inside of the forwarding process. What CEF does by default is it uses the source and destination IP. So it looks at the source is going to be 10.1.1.1 and 20.1.1.1. So they look at that as the source, and the destination is going to be 192.168.1.1, and that's for both of them. So each router is going to do a lookup process. The routing table is going to look it up, find out what interface to move it to that interface, and then from there it's going to find the layer 2 information of from the next router, use that information to rewrite the layer 2 header, and then forward it out the interface to the next router. And then the following router is going to do the exact same process until the packet finally either reaches its destination, runs out of time to live value, or reaches its maximum transmittable unit, or reaches its TTL value limit, or the router doesn't know how to forward that packet to wherever the destination is going. So it's a drop in the case of CEF. That is traditional. So what you can do is you can modify the load balancing hash. So, and I will actually bring up a router real quick to show you guys how this works. The way that this actually works is if we go to config T, we type in IP CEF ? And if you see where it says load sharing ? You can actually type in the algorithm, and by default it is universal. Algorithm for use in most environments. Now, what you can do is you can say use the original algorithm. You can say use the universal algorithm, or you can use what they call the include ports. Include ports means it's going to look at layer 4, not just layer 3. So what you would end up doing is you would look at source and destination port. So depending on how the connection was opened. So if this was a web server, then the destination port should be 80, right? And then these guys are going to generate some randomly high generated, so we'll say 35,000, just for the generality. So the way that it's actually going to look is it's going to look at the source and destination, and the port is going to be 10.1.1.1 colon 35,000, and the destination is going to be 192.168.1.1 colon 80. Now what's going to end up happening is traffic is going back and forth between the server and the client. The way that it's going to work here is this guy right here is going to maintain his port. This guy will always respond with this. The port destination, the originating port doesn't change because this was the destination. The source port never changes, because if this port changes, if this increments, so this becomes 1 or 2, that means that they may have one or more sessions open. So they may have one or more web servers or web pages open, or maybe one or more tabs open in Chrome or Firefox or something like that. That's where this comes into play. So when you have more than one connection, the difficulty that the original version of the CEF algorithm has the problem of is it just looks at source and destination IP. If you use include ports, it's going to figure out based on the type of traffic. So one session going to this guy, let's say this server does web, email, FTP, and DNS. So we're going to have 80, 25, 20, and 21, and we're going to have, 60, 63? No. I forgot the DNS number. How bad is that? 69? I think so. Whoa. I don't remember. How bad is that? Oh, this thing bugged out on me. There. Alright, so instead of doing that one, we'll that's the one drawback to OneNote. I don't know what I did to click on this. Draw. Alright, there we go. We'll use, what else can we use? We'll do SNMP. So 161. So these are the ports that it's going to be able to respond to services. So no matter what happens with the source IP and the port, if any session comes in here and opens up, all of these routers over here are going to be able to make a forwarding decision based on layer 3 and layer 4 information. So if this guy right here, if 10.1.1.1 opens up and says, I want to open up a connection, I want to send, I need to download a file. So it's going to be 10.1.1.1 colon 20. 21 I believe is management. 20 is the actual data. So if you have a connection open to an FTP server, the way that CEF is going to look at that is he might route it this way instead of going, and then if email is open, he might route it this way. And let's say, for instance, that the core here is actually connected. So we have a connection between the two routers. So, and then maybe web is routed this way. So let's use a different color. We'll say that blue is routed this way. And we'll say that red is routed this way. So, depending on how the traffic is routed, will determine how things are set up. So, or I'm sorry, depending on how the algorithm handles the traffic will determine how things are forwarded. Does that make sense? So CEF has a lot of flexibilities that the process, which is CPU switched, and fast switching, which is CPU then cached switched. And then we have CEF, which now you guys know how CEF works. That's the basic idea to it. So this is going to give you an overall idea of how things work with CEF and how to get traffic to work the way you want it to. It's not necessary to have things CEF switched. It's an optimization. Now, one little thing before I go and let you guys have the rest of the night off is, depending on how you're working with your traffic. So let's say, for instance, you're debugging. The reason I bring this up now is because it's on the top of my head. Debugging is a CPU service, meaning the CPU is going to go through and pull background processes to the front, to the user interface, Telnet or SSH, and let you see what's going on. So it's a background service that is it's bringing background services to the front so you can see what's going on. So whether it's going to be a routing issue, or you might have some sort of authentication mismatch, or whatever the case may be, debugging needs to be CPU switched or CPU handled. CEF is not CPU handled. So if you want to debug something, you want to debug traffic going from the router from here through, you need to turn CEF off here and here, and then you're going to be able to watch that traffic go through. You can't CEF switch and debug at the same time. However, if you would like to watch how traffic is going through here, you can actually take and use a Wireshark capture and watch this traffic as it's going through. You can use Performance Monitor, or you can use the iOS embedded packet capture, and you can look at it from that perspective, and then you can offload that information to Wireshark in a PCAP file, and that'll allow you to look at the traffic as it's going through. As a matter of fact, I'm troubleshooting an issue at work right now, and the issue is actually it's very simple. The problem is we have a user that when she's on the WAN or on the LAN, she cannot get to the Citrix server. Actually, she gets there, but the app on the Citrix server won't pull up. If she goes to the wireless, so I'll just draw a cheap wireless access point. If she goes to the wireless, she can. Now, I'm trying to figure out where the issue lays. She can get to the Citrix server from both computers, log in, authenticate, and all other good stuff, but to actually use the app doesn't work. So, trying to figure out what specifically the problem is, that's where the time-consuming part, and Wireshark has become my best friend now because I can break down on a per packet basis what's going on. So, but that is the extent of how CEF works. So, if you'd like to know more about CEF, I would definitely recommend looking up Cisco's documentation and seeing how it all comes to play, because it's going to be something that if you don't get it now, you're going to have a hard time down the road with it because of the fact of, and I believe, what is the iOS image? It is 12 for 20 and above. So this iOS image and up, fast switching has been deprecated. Is dead. So it's either processed or CEF. I always want to draw an either. I don't know why. CEF switched. So if you go before that, so 12, 4, 15, you're going to have all three options. So, but I'll get much more deeper into how this actually works when we get into the IP routing section, and I will go into detail on how that works. So, I hope this has been informative for you. I would like to thank you for viewing.